Hi everyone, this is Rajeshwar, Assistant Professor of EC Department at St. Martin Engineering College. Today I am going to discuss counters. So, counters are important topics in digital electronics. So, these are the contents of this topic. So, what is a counter? Type of counters, asynchronous counter and synchronous counter. Next, so, counter and its types. What is a counter? Counter is a sequential circuit which counts the number of pulses or events. Next, type of counters. Synchronous counter and asynchronous counter. So, it is also called as a ripple counter. So, other are up counter, down counter and a decade counter. So let me discuss first synchronous counter. So in synchronous counter, all the flip-flops are triggered at the same time and the output will be toggles. In the asynchronous counter, so only first flip-flop is toggles. So that is whenever we trigger with the input pulse, only the first flip-flop will be triggers and next onwards the output of the flip-flop will be toggles depend upon the output of the first flip flop. So it is up counter. So up counter is, so it counts the from 0 to it counts 0 to like so 1 2 3 like etc. So this is the up counter. Coming to the down counter, it starts the count from 0, or it may be, for example, it is 4-bit counter. It starts a count from 3 to up to 0, like that. So up down counter, we can count the up count and down count, that is ascending and descending count. So decade counter, in this decade counter we can count the number of states will be 10. Number of states will be 10, that is it counts 0 to 9. Next, coming to the 2-bit synchronous counter. A 2-bit synchronous counter is required 2 flip-flops. A 2-bit synchronous counter requires 2 flip-flops. It requires flip-flops and it counts 4 states. It counts 4 states from 0 to 3. So let me explain with the example. Initially, I am assuming the states of the flip-flops. So initially, this state is 0 and 0. So that is QA, QB. So again, clock. Initially, I am assuming so states of the QA and QB are 0 and there is no clock initially. So whenever I applied first clock, so whenever I applied first clock, so what will happen? So the logic of the JA equal to KA equal to 1, and here also to toggle the flip flop we need JB equal to KB equal to 1. So whenever I applied first flip flop, so the 0 will be toggles to the 1. Okay, here previously this value is 0, so that is JB equal to KB equal to 0. Due to the J and KB value is 0, there is no toggle. So whenever I applied first clock, first clock, so the QA value will be toggles to the 1, and due to the JB equal to KB equal to 0, the output of the QB remains unchanged and it will be 0. It will be 0. So the states will be changes. Now the states of the QA is, the states of QA is 1. The states of QA is 1. So that is JB equal to KB equal to 1. Okay. So QB is 0, QA is 1. Whenever I apply second clock pulse, second clock pulse. So due to the JA equal to KA equal to 1, the first flip-flop will be toggles to the 0, so that is QA equal to 0. So as JB equal to KB equal to 1, this will be toggles to the 1. The new states are 0 and 1 after applying the second clock. So next, the states of the flip-flops are again changed. The new states are, so QA equal to 0 and QB equal to 1. So now I am applying third clock. So when I applied third clock pulse, so this is JB equal to KB equal to 0. Okay. So as the JA equal to KA equal to 1, so the first flip-flop is toggles, that is QA will be 0 to 1. As JB equal to KB equal to 0, the output of QB remains unchanged. So the new states are 1, 1, 1, 1. So the states are again changed. The states are again changed to the 1, 1. The states of QA is 1 and QB also 1. So this 1 makes JB equal to KB equal to 1. Already we have JA equal to KA equal to 1. Whenever I applied fourth clock pulse, so as JA equal to KA equal to 1, so applying of the pulse, so this state will be enter into the 0, and here also JB equal to KB equal to 1, the output will be 0. So that is outputs are 0, 0. See here, after fourth clock pulse, after applying the fourth clock, so the output will be goes to the same state. That is again it will be 0. I'm switching on to the next slide. So this is the 2-bit synchronous counter. Okay, this is truth table. Initially there is a 0, 0. So after applying the first clock pulse, the state of the QA will be 0, so 1, and QB 0. And after applying second clock pulse, so this is 0, 1, and after third clock pulse 1, 1. After applying the fourth clock pulse, so the counter will be reset to the 0. The counter will be reset to the 0. So next I will discuss. So these are the timing diagram of 2-bit synchronous counter. So whenever we applied the first clock pulse, so after applying the first clock pulse, So it is first negative triggering pulse occurs. So until then QA value will be 0, and whenever we apply the first clock pulse, the output goes to the 1. That is the positive pulse we will get. Positive pulse we will get. So as QB is depending upon the output of QA, okay, so it is working on a negative edge triggering. So whenever the QA output will be negative trigger, the QB will be toggles. The QB will be toggles until until the so QA will be shift to the next clock. So this is initially QA is 0, QB 0. When QA is 1 and QB will be 0, we can see here QA QB 0 0, that is equivalent to the decimal 0. Here 0 1, that is equivalent to the decimal 1, and here 0 1. So this is equivalent to the decimal 2. So this is the regarding the 2-bit synchronous counter. Next. So I will going to discuss the 3-bit synchronous counter. So this is the 3-bit synchronous counter using T flip-flop. So for 3-bit we need 3 flip-flops. We need 3 flip-flops, and we will get the 8 states. We will get 8 states. That is, we can count 0 to 7. We can count values from 0 to 7. So as this is a synchronous counter, we cannot draw the directly this 3-bit synchronous counter. So we have to design this 3-bit synchronous counter using the T flip-flop. So there are some steps. We have 5 steps to draw the 3-bit synchronous counter. Step 1. This is step 1. So we have to decide the number of flip-flops. As it is a 3-bit counter, we require 3 flip-flops. As we discussed. So as it is a 3-bit counter goes to the 8 states, and it can count from 0 to 7 or 7 to 0. This is the first step to design the synchronous 3-bit counter. Coming to the step 2. So we need excitation table for T flip-flop. So this is the excitation table for T flip-flop. Whenever present state 0 and next state 0, there is no toggle. That is, we are indicating with the 0. Whenever present state is 0, next state is 1, so this will be 1. Toggle equal to 1. So it toggles the output. Next, when present state is equal to 1, next state equal to 0, we will get the toggle equal to 1. And there is 1 1, we will get the 0. So this is the excitation of T flip-flop. Next, so step 3. So we need state diagram, state excitation table. So this is circuit excitation table. So we need state diagram and state table. These are the states. As I discussed, the states are we have 8 states. So state from 0 to 7, it counts 0 to 7. So that is 0, 1, 2, 3, 4, 5, 6, 7. So as it is a counter, it counts in a sequence. So it is a present state. For this present state, the 1 is the next state. So this is a state diagram. From this, we can write this state table. So this is binary equivalent 0 0 0. So this is 0 0 0, and that next one is 0 0 1. So this is the state diagram. This is a state table. and we have so circuit excitation table. From the previous one, so we can write that circuit excitation table from this state diagram. So this is present table, present state. So for example, this is 0 0 0. For 0 0 0, so what is the next state? So this will be 0 0 1 is the next state. So we can see here, so present state is 0 0. So present state is present state is 0 0 0 and next state will be 0 0 1. Next state will be 0 0 1. So we can write this present state and next state in the circuit excitation table from the this state diagram. So we can write the circuit excitation table from the this state diagram. So next for 0 0 1, so next state is 0 1 0, like that. So we have to write the excitation table for the flip flop. So in this we have to design, so in this we have to design the TA value, TB value and TC value. So we cannot take that directly as in the synchronous circuit, directly QA value, QB value, like we cannot take the directly. So we can design this inputs of the 3-bit synchronous counter. From the excitation table, we have to derive the TC value, TB value, TA value. So as we know from the excitation table of T flip flop, so we have to write the TC value, TB value, TA value. Okay, from the T flip flop excitation table, so by comparing the QC value and QC plus value, we can write the TC value. Same, see here 0 0, so it is a 0 from the excitation table, and again 0 0, it will be again 0. So this is again 0 0, again TC value is 0, and this is 0 1. There is a toggle in the output, that is TC equal to 1, that is TC equal to 1. Next here 0 1 1 1, there is no toggle, so TC equal to 0. Next 1 1, there is no toggle, it is a 0. And next again 1 1, there is no toggle, so this is again 0. So last state 1 1, sorry 1 0, so there is a toggle. Okay, so it will be 1. From this we can write, K map. So step 4 is K map. So that is for TC, so it is, so from the truth table, that is, so we can write 0 0 0 1 0 0 0 1 and 0 0 0 1. So map it. So after mapping, so here QC values are varied, so there is no need to take off QC value. So here only mapped in the 1 1, that is we can write QB QA. Now we have the TC equal to QA QB. Same from the this circuit excitation table, so draw the K map for the TB. So right, so point out the ones and map it. So that is map. This is a quad. So here the values of QC are changed. So here is no need to take the QC value. Here the QA is the common. Write QA. So that is, so TB equal to QA. Next from the circuit excitation table, so draw the K map for TA. So here TA equal to, so all the ones are mapped, all the ones are mapped, that is we can write directly TA equal to 1. So this is the K map for TC, TB, TA. Next, so from that K map, so already we know TA equal to 1. So just give the TA equal to logic 1, TA equal to logic 1. So we have TB equal to, we have what is TB equal to QA, TB equal to QA. Just TB equal to QA, give the TA value directed to the TB. Next, for TC equal to, we have TC equal to QA QB, QA QB. So TC equal to, so take QA value and QB value and take a AND gate and give it to the, okay, TC. So this is the design of 3-bit counter. Next, so design of 4-bit synchronous counter using the JK flip-flop. Okay, before going to this one, I will explain, this is through a video. Let me explain that through a video. So this is a video regarding 4-bit synchronous counter. We have 4 flip-flops here. Okay, the clock is applied to the all the flip-flops here, all the flip-flops here. So whenever applied first clock, the output initially it will be 0. So it will be 0 0 0 after applying the first clock. So as the J and K values are 1 1, so first flip flop only toggles. So that is we will get the 0 0 1. We will get the, what is first one? So we will get the, we will get the 0 0 0. Okay, next.
And this purple system also J and K. So the output of,
So after applying the second clock pulse, so after applying the second clock pulse, so already this is J and K values are 1 1. The output will be toggles to 0, and previously this is 1 1. Let me show that. So these are the, you can observe here. Previously these are the 1 1. Okay. After applying the next clock pulse, so it will be become 1. That is, whenever the J and K values are 1 and applying the K value, the output will be toggles. So now we get a 0 0 1 0. So this is the decimal equivalent to. Let us continue with the video, and so here we will get the 0 0 0 1 0. Here we have, this will be 1 1. So whenever we apply the third clock pulse, so here is 1 1, other JK values are 0 1 0 1. So these are the not satisfying the toggle condition. Whenever this is 1 1, by applying the third clock, whenever we apply the third clock pulse, so this will be unchanged and this will be changes, that is 0 0 1 1. We will get the, okay, 0 0 1 1, that is decimal equivalent 3. Okay, next see here, here 1 1 is there, 1 1 is there. So whenever we apply the fourth clock pulse, there is a toggle in the output of this one, and this is also toggles, this is also toggles. We will get the 0 1 0 0. We will get the 0 1 0 0 by applying the fourth clock pulse. You can see here. So after applying the fourth clock pulse, the outputs are 0 1 0 0. Okay, next continue with the video. Okay, so this is again, this first flip flop is 1 1. Okay, this is 0 1 0 1 0 1. So there is a chance of toggling of the first flip flop only. So that is after applying the fifth clock pulse, only the first flip flop output is toggled. The first flip flop output is toggled. The other flip flops remain constant. There is no change in the output states. So now we have 0 1 0 1, that is equivalent to, okay, decimal 5. Okay, next state. Now we can observe here. So the JK values 1 1, and here also 1 1 0 1 0 1. Whenever we apply the next sixth clock pulse, the position of the first flip flop, the state of the first flip flop and second flip flop will be changes. So again there is no change in the outputs of so this third and fourth. Why? Because there is no condition j equal to k equal to 1. They are not satisfying the toggle condition j equal to k equal to 1. Here we have j equal to 0, k equal to 0, and here j equal to 0, k equal to 1. So whenever we apply the next sixth clock pulse, so the bits here first bit and second bit will be changes. That is, so these two flip flops are obeying the j equal to k equal to 1. Here j equal to k equal to 1.
It also has j and k to be 1, so the output.
So this is, so whenever we apply the sixth clock pulse, after applying the sixth clock pulse, we can observe that, so this both bits are only changed, that is toggles to the, so previously it is 1, it is 0, so it is 1 and 0. So this is now 0 1 1 0, it is a decimal equivalent to, okay, 6. Okay, next. So here you can observe, so here this flip flop jk values are 1 1, this jk values are 1 1, and here and j and k values are 1. All the flip flops jk values are 1 1 1. Okay, whenever we apply the next seventh pulse, so this first flip flop output will be changes, and second and third and fourth. So this is a working of the 4-bit synchronous decade 4-bit synchronous counter. So it counts whenever the j equal to k equal to 1, otherwise there is no change in the output of the flip flops. Okay, we will see the other clocks. So this is applying the after 8th clock pulse. So this is after applying the 8th clock pulse. So 8th clock pulse, so that is 1 0 0, and for 9 1 0 0 1, and for 10 and 11. So that will be counts automatically whenever we apply the clock pulses. So let me write whatever we have discussed today. So okay, we have discussed synchronous counters, synchronous counters. Okay, we have discussed 2-bit synchronous counter, and we have designed 3-bit synchronous counter using T flip flop, and we have seen 4-bit analysis of 4-bit synchronous counter, and other counters are like up counter, up down counters, and decade counter, and ring counter, and Johnson counter. These are the other topics in the remaining class. So what are the remaining? Up down, decade counter, ring counter, and Johnson counter. So thank you for watching.